All right, have you ever stopped to think about how your GPS just knows the fastest way to get somewhere? Or how a social network is so good at suggesting new friends? Well, it's not magic. It's something called discrete mathematics. And today, we're going to crack open this hidden world using these amazing handwritten notes as our map. So, let me ask you something. What in the world do your friends on social media, the route a delivery truck takes, and, I don't know, a complicated seating chart for a wedding, what do they all have in common? Well, believe it or not, they're all puzzles. They're puzzles about arrangement, about rules, and about connections. So think of it this way. We're going to build a kind of toolkit today. And in that toolkit, we're putting three essential tools from discrete math that'll help us solve exactly these kinds of problems. Okay, tool number one. This is a big one. It's called combinatorics. And really, it's the art of counting without actually counting. I know, sounds weird, right? But it's for when you have way too many possibilities to list out one by one. It's like a super powerful shortcut for answering the question, how many ways can we do this? So, inside combinatorics, you've got these two key ideas. First, permutations. Here, the order is everything. It matters. Think about a word. CAT is totally different from ACT. But then you have combinations, and here the order just doesn't matter at all. If you're picking a team, choosing Anne, Bob, and Carol is the exact same team as choosing Carol, Bob, and Anne. And getting this difference is so crucial. It's the bedrock for everything from figuring out odds in a card game to building secure encryption online. Okay, let's get real for a second. We're going to grab a problem straight from these notes. Picture this. You've got 12 people. You need to pick a committee of 4. Now, does it matter if you pick Sarah first and then John, or John first and then Sarah? Nope, it's the same committee. So ding, 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 it's a combinations problem. The big question is, how do we figure this out without writing down every single possible group? Because that would take forever. And the answer is 165. That's it. 165 different ways. We didn't list them, we just used the formula from the notes, and boom, a few quick steps and we have our answer. And that is the magic of combinatorics. We found the exact number without doing the impossible task of listing every single option. We counted without counting. Pretty cool, right? All right, so that's tool number one. For our second tool, we're going to level up. We're moving from just counting things to actually creating whole systems with their own internal logic. These are called algebraic structures. The best way to think about them, it's like you're writing the official rulebook for a brand new game. And this definition from the notes really says it all perfectly. An algebraic system, it sounds intimidating, but it's just two things. You have a set of items, like numbers, and then you have a set of operations, which is just a fancy word for rules on how those items interact, like, say, addition. That's it. So simple, right? But from this one simple idea, we can build these incredibly powerful, predictable structures. And we can actually build these systems step by step by adding rules, creating what mathematicians call a group. Let's just walk through it with something we all know, adding whole numbers. Okay, rule 1, closure. If you add 2 whole numbers, you always get another whole number, right? You never leave the set. Rule 2, associativity. The way you group the numbers doesn't change the final answer. Now we're up to what's called a semigroup. Okay, rule 3, identity. There's a special element like 0 that doesn't change anything when you add it. Add that rule in, and now you've got a monoid. And finally, rule 4, inverse. For every number, there's an opposite that cancels it out, like 5 and -5. Once you have all 4 of these rules in place, congratulations, you've just built a complete, self-contained system. You've built a group. Okay, on to our final tool. And this one is my favorite because it's so visual. We're talking about graph theory. Now, when I say graph, don't think bar charts or pie charts from a business meeting. No. This is about one of the most powerful ideas in all of modern computing, how we visualize and analyze connections between, well, anything. Okay, so take a look at this. At first glance, it might just look like a random doodle, right? Some points and lines. But this is a map. It's a network. Those points, they could be cities on a map, computers on the internet, or even people in a social network. And the lines? Well, those are the connections between them. Graph theory gives us the language to actually talk about and work with these networks. And the basic building blocks here are so simple. The dots, they're called vertices. The lines connecting the dots, they're called edges. That's literally it. Just with those two concepts, vertices and edges, we can model almost any network you can possibly imagine. And, of course, that leads us to the million-dollar question. Once you've mapped out your network, how do you find the best way to get from point A to point B? In other words, what's the most efficient path, the shortest route? Well, the solution, as you can see being worked out in the notes here, is to assign a cost or a weight to every single connection. That cost could be distance or travel time or anything really. Then, all you have to do is find the path where the sum of those costs is the absolute lowest. There are these incredibly powerful algorithms like Dijkstra's that are built to solve this exact problem by just systematically exploring the network to find that one perfect route. And for the puzzle on this page, the shortest path adds up to a total cost of 24. Now, this might seem like a simple little puzzle, but this is exactly the same principle your phone's GPS uses to navigate a massive, complicated city grid and get you home the fastest way possible. So there you have it, your Discrete Math Builder's Toolkit. 3 incredibly powerful tools. We've got combinatorics to help us count all the possibilities. We've got algebraic structures to create systems with crystal clear rules. And we have graph theory to map out and analyze all the connections. Put them all together, and you can start to tackle some seriously complex problems. So you see, discrete math isn't just about numbers in a textbook. It's the hidden logic. It's the operating system that runs our entire modern world. The next time you use a search engine or get a package delivered, just take a second and remember what's going on under the hood. It's not just code, it's this beautiful, elegant world built on the logic of arrangements, rules, and connections. So now that you have the toolkit, what hidden systems are you going to start seeing all around you?